Students, in this session, we are going to see about the capacitance of a parallel plate capacitor with compound dielectrics, not a single slab of dielectrics, a multiple slab of dielectrics are connected. Let us see the first category, if all the dielectrics are connected in series arrangements. So this is a upper plate, this is a lower plate of the capacitor, top plate and bottom plate. So in between, there is a dielectric slabs are connected in series arrangements. So the K1 is a dielectric constant of the first slab, K2 is a second slab dielectric constant, and K3 is a third slab dielectric constant, and so on. For a nth slab, it is a Kn. Similarly, the thickness of the first dielectric slab is T1 and T2, T3 and Tn, and so on. So the distance between the two parallel plates is as it is d. So as we know that the capacitance value of the parallel plate capacitor when the dielectric slab is inserted, the formula is C is equal to x lambda naught A d minus t plus t by k. That is, we are in the previous sessions itself we are derived this equation. So x lambda naught A is the same because A is the area, this is the area. So the area of the dielectric constants are, all the dielectric material slabs are same. So but d minus this t is a combination of all the thickness, that is a T1 plus T2 plus T3 up to Tn. So we have to put instead of T1 plus T2 plus T3 etc. up to Tn, plus instead of this T also we have to put T by K means T1 by K1 plus T2 by K2 and T up to the Tn by Kn. Since the dielectric materials, the dielectric slabs, the n number of dielectric slabs are inserted, placed in the parallel plate capacitor which is completely covered. So the D is equal to T1 plus T2 plus up to, so that is this thickness and the parallel plate thickness are same. Hence these two are equal means this D minus this T1 plus T2 plus T3 up to Tn is become equal 0. So this term will not come, it is a 0. So x lambda naught A by T1 by K1 plus T2 by K2 up to Tn by Kn, where K1, K2 and Kn up to Kn are dielectric constant of the all the dielectric slabs, and T1, T2 are their respective thickness. So this is the formula for the dielectric slabs are connected in series arrangements, which shows the change in capacitance of the parallel plate capacitor. Dear students, similarly for that same dielectric slabs are connected in parallel type arrangements, that is like this. So listen, so this is the upper plate and the lower plate. The dielectric slabs are connected in parallel way, arranged in parallel way. The K1, K2, K3 up to Kn are the dielectric constants of the respective dielectric slabs, but the thickness, this D will be same, but area is differ. So this is the area of the plate. So the area of the first slab is A1, second slab is A2, A3 up to AN. But in series arrangements, A is same but thickness only changed. So keep in your mind. So as it is a series parallel arrangement, C is equal to C1 plus C2 plus C3 up to Cn. So C is equal to, for the first slab x lambda naught A by D into K, because when the dielectric slab is inserted, the capacitance value is increases by dielectric constant time. So x lambda naught A1 D into K1, x lambda naught A2 D into K2. So we have to add all the individual change in the capacitance value after the dielectric slab is inserted. So when A1, A2, A3 are the same, that means all the areas are equal. This area and A1 and A2 are equal, and then it is equal to A3 up to AN. So finally we get what is the area? A by N. So you substitute instead of this one x lambda naught by D. X lambda naught by D is a common, you taken outside, and A by N is a adding, it is also taken outside. The remaining thing K1 plus K2 plus etc. up to Kn. So we get only the summation of all the dielectric constants. So this is the change in capacitance of the parallel plate capacitor after the n number of the dielectric slabs are arranged in parallel type. So this is a formula. So note down this also. Dear students, in order to understand the parallel and series arrangements of the dielectrics, let us see the problems. So between the parallel plates of the parallel plate capacitor of area. So the area of the parallel plate capacitor is A, and a copper plate sits on the dielectric slab of dielectric constant K is equal to 2 as shown in the figure. That is, this is a capacitor upper plate and lower plate. Then we have the dielectric constant, the copper. So in the question itself, copper plate sits on the dielectric slab. This is the dielectric slab of the dielectric constant K is equal to 2. The copper plate is sit on it. So the copper plate means it is a metal conductor. The dielectric constant K value for the metal will be, it is infinity. So this is a free space. So let us be considered the three capacitor D. We have a three dielectrics. 1, 2, that is a three different materials are connected. Let us see what about the change in first capacitor. So C1 is equal to x lambda naught, that is x lambda naught A by D. That is formula. We should remember the change in capacitance, which is equal to previous capacitance into the dielectric constant. So the C naught is x lambda naught A by D. So what is the thickness of this each capacitors? It is a D by 3 only. So D by 3. So the K value is, what is this K dielectric constant for this dielectric slab? 2. So 2 into x lambda naught A D by 3. So we get 3 will become the numerator, 6 x lambda naught A by D. Similarly for the second one, so it is K into x lambda naught A D by 3. That is C naught is x lambda naught A by D. The thickness is D by 3. So x lambda naught A by D by 3 into K. So you have to bring this 3 in the numerator, 3K x lambda naught A by D. So for the third one, it is a nothing else. So simply x lambda naught A by D is a capacitance value. D is a D by 3. We get 3 x lambda naught A by D. So just by seeing the diagram itself, by using a simple formula C is equal to C naught K, we are able to derive this C1, C2 and C3. But these three are connected in series arrangements. So the formula for series arrangement of the capacitance are 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So 1 by C, which is equal to, what is the C1? C1 1 by means we have to take the reciprocal, D by 6 x lambda naught A, and for C2 D by 3K x lambda naught A, and for this one D by 3 x lambda naught A. As we know that this second one is a copper plate, so the dielectric constant value is infinity. So anything by infinity is 0. This second term become 0. Only we have to add these two things. Yes, as shown earlier, the middle term becomes 0. So the first term and the last term we have to add. So by simply adding the D by x lambda naught A is taken outside, taking the LCM of 1 by 6 plus 1 by 3, we get the answer 1 by 2. That is, we have to take the reciprocal of the both the terms, then only we get the effective capacitance. C is equal to 2 x lambda naught A by D. This is the final change in capacitance value after the insertion of the dielectric constant under the copper plate. Yes, dear students, we will see the next problem. So find the ratio of the capacitance of the capacitor filled with two dielectrics. So there is a two dielectric material of the same dimension, but the dielectric constants are K1, K2. So we have to find the ratio of the capacitors. So we may fill the two dielectrics either in parallel as well as in series. So we have to find the values for parallel as well as the series, and then we have to take the ratio of the two capacitance value. So this is a parallel connection, K1 and K2, and the series connection, K1 and K2, dielectric constant K1 and K2, two dielectric slabs are connected. So as in the parallel case, Cp is equal to C1 plus C2, then Cp which is equal to, what is that, x lambda naught, what is the area only differs, it is the same dimension, half it will take, so A by 2 K1D. So we should remember that whenever the dielectric slab is inserted, the change in capacitance is K times of the original one. So this is the original one and K times K1. For the second one, it is x lambda naught A by 2 by D into K2. So students, very clear, just you put the x lambda naught A by D formula. For A, you have to substitute A by 2, and K means K1 here, K means K2. By adding, we get that x lambda naught a by 2d, which is equal to x lambda naught a by 2d, x lambda naught a by 2d. So k1 plus k2 is taken. So this is the effective capacitance for the parallel arrangements. If the same two dielectrics are connected in series, what is the effective capacitance? So 1 by Cs, which is equal to 1 by C1 plus 1 by C2. So 1 by Cs, which is equal to C means x lambda naught a by d. So x lambda naught a by d. So we have to multiply with the dielectric constant k. It is the first capacitance k1. So that thickness is d by 2. Why? Because if it is connected in parallel, the thickness is divided. Sorry, if it is connected in series, the thickness is halved, and if it is connected in parallel, area is halved. So only we put d by 2, and here it is a second capacitance, dielectric constant k2. So we take the reciprocal. This d will become the numerator, and this 2 will come here. So 2 x lambda naught a by k. Hence we arrive the equation as a Cs, which is equal to 1 by Cs, which is equal to d by 2 x lambda naught a. So 1 by k1 plus 1 by k2, we have to take the LCM for this 1 by k1 plus k2, we get k1 plus k2 by k1 k2, and finally we arrive the equation k1 k2 by k1 plus k2 into this equation. This is a reciprocal. We have to take the reciprocal. So what is the question? The question is take the ratio. Just merely take the ratio of the parallel and series arrangements. Just to cancel all those things, we get the equation k1 plus k2 the whole square by 4k1 k2. If you substitute assume that k1 is equal to 2 and k2 is equal to 3, we get the answer 25 by 4.